Check it out now, y'all.
nanoHUB-U, online instruction.
So in the last lecture, we discussed the essential parts or components of an atomic force microscope. And in this particular lecture, we'd like to run through a discussion of the types of calibrations that you might consider performing once you have a microscope that's up and functioning. So there are, in principle, 4 calibrations that are required to obtain reliable data from an atomic force microscope. These 4 calibrations are the calibration of the spring constant of the cantilever. We need to also calibrate the sensitivity of our photodiode, that's the optical system. We need to focus on an XY calibration scale to map out the voltage applied to the translation stages in X and Y, translate those voltages into actual displacements in nanometers. And then lastly, the Z calibration that's going to give us the information about the distance between the tip and the sample. That also has to be worked out. So what I'm going to try to do is explain some traditional calibration techniques that are often used, and hopefully with this background you can then go and check your own instrument and see how well it might be calibrated. The first issue is the calibration of the spring constant of the cantilever. Spring constant of the cantilever is designated by the parameter K, and K in principle can be written down. There's a closed formula, or an exact formula for the spring constant K of a cantilever. It involves the elastic modulus E of the material from which the cantilever is made, and then there are parameters that describe the dimensions of the cantilever, the width, the thickness, and the length. Now, we'll derive this equation in week 4 of the course. Right now, we're just stating it. But the problem is that if you try to evaluate that expression for any typical cantilever, you'll find that the T cubed term, the thickness cubed term, dominates. And that's simply because you don't accurately know the thickness of the cantilever. It's on the order of a micron or so. The width and the length of the cantilever can be measured in a scanning electron microscope. And usually those parameters can be reasonably well controlled, but the thickness can be off. And if the thickness is off by a little bit and you cube that quantity, then your expression for K, calculated strictly from a geometrical approach, that expression for K is invalid. It's no longer accurate. So there are a variety of ways to calibrate K, and they all require a dynamic approach to a cantilever. And so what we're going to do is we're going to postpone the calibration of K to part 2 of the course, which deals more with the dynamics of cantilever motion than part 1 of the course. But the 4 techniques that are often used are just listed here for you to, just for reference purposes. I'm often asked, why is there such a variability in the spring constant K? And very early on, when we started to do work with cantilevers, commercially available cantilevers in our lab, we actually bought a wafer of cantilever chips. That wafer contains many chips, and each chip contains something on the order of 3 to 6 cantilevers per chip. So there's thousands of cantilevers available. And what we did is we systematically kept track of the spring constant K for each of the cantilever chips in the wafer. And what we found was that the cantilever chips from the middle of the wafer reasonably well met the manufacturer specifications. In other words, there wasn't a whole lot of variability between the spring constants measured for, let's say, the cantilevers localized in the middle of the chip. But as you started to choose cantilevers out towards the perimeter of the wafer, there started to be significant deviations in the spring constants that we obtained. And those deviations or variabilities in the spring constants could be directly related to the non-uniformity of the processing conditions that existed when that particular wafer was formed to make the cantilevers. So in our opinion, this is anecdotal. We never published anything on it, but we had a very strong feeling that if you just buy a few chips if you just buy a few cantilever chips, and they come to you in a box, you have no idea where those cantilever chips are taken from the wafer. And so therefore, depending on how well the process conditions are controlled, you can have a wide range of spring constants, even for cantilevers in one box. They can be chosen from different parts of the wafer, and that's why you have to go through a calibration if you're doing careful work. I found a recent study that I found very interesting. This study basically used the exact same 30 cantilevers on 10 different chips. And these chips were sent around to different labs. In fact, I think there were maybe 10 different AFMs used to calibrate the spring constant of these cantilevers. The calibrations were performed on the identical cantilevers, and the results are then plotted on this chart. And what you can see is that even though different companies or different research groups are using AFMs from different companies to calibrate the cantilevers, and even though the cantilevers used in this study are identical, right, there's still a range of K values that are achieved by these calibration techniques that will be discussed in part 2 of the course. So I think it's really hard to obtain a cantilever with a spring constant, known spring constant, to better than about plus minus 10%. I think that's the conclusion that you have to draw from this particular study. And if you're interested in more of the details, please look up the reference that I give here. As always, seems to be in AFM an infinite number of issues that have to be resolved if you're really doing very careful work. And I just wanted to mention a few of those issues here. Typically, the cantilever is pitched. There's a pitch angle of the cantilever with respect to the substrate, and this is intentionally done in order to get the laser beam to reflect off the cantilever into a photodiode. And typically that angle is on the order of 7 to 20 degrees. Different companies have different values, but typically it's between 7 and 20 degrees. Well, that angle, if you follow it through logically, that angle will affect the spring constant K that you measure, right? And so if you're really doing careful work, you have to take that cosine squared of that angle into account in order to get corrected expression for the cantilever spring constant. You also have to ask the question, where is the force being applied to the cantilever? Force is, of course, applied to the tip that's mounted on the cantilever. The tip is never at the end of the cantilever, so just knowing the length of the cantilever doesn't necessarily tell you where the force is applied. So maybe you have to worry about an effective length if you're trying to use the numerical formulas that were given earlier on in this slide, in this lecture. And then also where the laser beam is positioned on the cantilever will also change your estimate of the spring constant, right? So this is presumably this effect of where the laser beam is positioned on the cantilever. This has some bearing on why different AFM pieces of equipment give different values for K, even though they're all using the same cantilever to make a measurement. So again, careful work requires a lot of issues that have to be sorted out, and it's worth mentioning those up front just so you're aware of it. The second calibration technique is the sensitivity of the optical system of your AFM. So this optical sensitivity, coupled with the spring constant K of the cantilever, determines how accurately you can measure forces in your atomic force microscope. And there's a rather elaborate calibration that you have to go through if you want to calibrate the sensitivity of the optical system. And I try to go through that in this slide. Basically, if you approach the substrate to the cantilever tip, and if the substrate is very hard, you'll map out something called a force distance curve, force displacement curve. The displacement is in volts applied to the z-piezo. The y-axis of this curve is a voltage that comes out of the position-sensitive photodiode. So you don't have any useful data because everything's in volts. Depending on how carefully you've positioned your laser on your position-sensitive diode, the force versus distance curve won't even be centered at some v equal to 0, right? So it'll be floating off in space. And so the first step that you have to do is you have to translate that force versus distance curve so that it's calibrated in the z direction. So that's usually done by relying on the z calibration of the z-piezo. And so you can go from panel B to panel C in a very straightforward way. The trouble is the y-axis in panel C here is again not calibrated. It's just the voltage coming out of the position sensitive photodiode. What you need to do is you need to turn that voltage into a displacement of the cantilever Q, right? And so the way that's done is by measuring the slope of the curve after the tip makes contact with the substrate, and using that measured slope, in fact it's the inverse of that measured slope that gives rise to this parameter called S, and this parameter called S can then be used to multiply the voltage out of the position sensitive photodiode to actually get a displacement of the cantilever, and that displacement is shown in panel E of this slide, right? So if this calibration is done properly, and if your substrate that you use when you do this calibration is very hard, right, the slope of the calibrated curve is going to be 1, right, or -1 technically, because as you push the substrate towards the tip by a distance z, the cantilever is going to deflect by a distance q. There's no indentation because the substrate is very hard, and so you know you've done this calibration properly if the slope of the curve after the calibration's been performed is precisely -1. And so then once you know that the deflection of the cantilever Q by measuring the optical sensitivity S, then you can multiply the displacement of the cantilever by the spring constant K to actually get the force that the tip is exerting on your sample, and that's shown in panel F here. So this calibration is automated in many new systems. In the old days we had to do it by hand, but nowadays it's pretty straightforward, and it's probably worthwhile for you to think through these steps so that you can understand what the CAN software in your atomic force microscope might be doing when you actually calibrate these force versus distance curves in this way. So this gives the optical sensitivity, basically how many volts is produced per nanometer deflection of the cantilever using this beam bounce technique. The third calibration is calibration of the X and Y scanners, and this calibration is usually performed by purchasing a grid-like pattern that many companies now sell, This grid-like pattern is comprised of square plateaus. The square plateaus have a well-defined periodicity P, which is built into the system when, or built into the chip when the chip is actually made. And if you want to render that diagram in an atomic force microscope image, you'll end up with a image that kind of looks like the picture with the blue background here. Right, now once you obtain that image, then you can do all kinds of things, right? You can, for instance, check and make sure that the periodicity in the X direction, the periodicity in the Y direction are the same. You know the periodicity because the chip has been made and is with a certain accuracy, right? You can also check to see if your X scanner and your Y scanner are orthogonal to one another. This means that the patterns that you obtain in your AFM image should be at precisely 90-degree angle. If they're not, there's a non-linearity, or there's a coupling between your X and Y scanners, right? They're not oriented at right angles with respect to one another. So that non-orthogonality of the XY scanners, that will be important if you're doing experiments that require you to measure precise angles between features in your substrate. If you're not particularly interested in the relative orientation of, let's say, two features on your substrate, then maybe this orthogonality check isn't so important for your work. It's important to realize that depending on the age of your AFM, the technology that's gone into the X and Y scanners, right, you can actually have very nonlinear X and Y images you can have very nonlinear calibrations that come out of this type of an experiment. So in this particular case, I show the result that you would get if your X and Y scanners are linear over the region that you scan. Right? If they're linear, then the size of the features observed anywhere in the image should be identical one with respect to another. If you've got a nonlinearity in one direction, let's say in the X direction, then the size of the features that you measure are going to depend on where that feature is in your image. So I've tried to indicate that by the dashed green boxes in the middle panel. And then lastly, you can have a situation where the scanners are both nonlinear in X and Y, and if that's the case, then the size of the features are going to depend not only in the X position but the Y position of the feature in your image. So this is something that if you purchase one of these calibration gratings, this is a pretty easy thing to check, and gives you some confidence that your instrument's performing properly. There could also be a coupling depending on how the motion is achieved. In principle, there could be a coupling between X and Z and Y and Z, and it's important to understand that coupling and at least be aware of the system that you're using, whether this is an issue or not. How do you check for this XZ or YZ coupling of scanners? Well, again, you would have to purchase a chip which has triangular features associated with it. These triangular features have to have a known angle, which I indicate by theta naught in the upper left diagram here, right? Typically, these triangular-like features, they're produced in a silicon 111 substrate just by the natural anisotropy and the etching procedures for these silicon substrates. And I think for the silicon 111 substrate, that angle theta naught is about 55 degrees. So to check for this coupling, what you would then do is you would scan, you would orient your calibration chip in such a way that you can scan as indicated by that white arrow in the upper right corner, right? And after you've performed that scan, then you would go back and you would investigate the angle that those features make, right? So I I try to indicate that ideally you would expect to see features that make an angle with respect to the horizontal of theta naught. That's indicated by the black traces in the bottom right panel of this slide. Experimentally, you may actually find that the angle is some value theta sub m, so it's distorted from the value that it should be, right? If that's the case, then there's a coupling beta that's given by 1 minus the tangent of the two angles, so I've indicated in the yellow slide. So this coupling beta is then would then have to be programmed into your controller in order to correct for this particular feature. So this would calibrate your scan in, let's say, the x direction. If you wanted to check your y direction, in other words, the YZ coupling, you would just have to rotate the grating and perform the measurement for the Y scanner. Calibration of the z-piezo is the last topic in this particular lecture. Again, to do this, the easiest thing to do is possibly to purchase a calibration standard. Calibration standard would consist of features, rectangular features with a known step height h. It would be up to you to pick the height h to match the experiments that you're doing. So if you're doing experiments with where you're trying to measure z heights on the order of 1,000 nanometers, then it wouldn't make much sense for you to purchase a grating which has a step height of, let's say, 20, 25 nanometers. So you have to match the height of the grating to the particular experiments that you're trying to do. After you achieve an image, after you obtain an AFM image of that particular calibration grating, you can then use a histogram analysis, right? Don't draw a line across the image and then try to measure heights from that particular line. That's not very accurate. It's much more accurate to define a region on the substrate, use that region of the substrate to produce a histogram of heights, as I've indicated in the bottom right hand curve, bottom right hand portion of this slide. And from that histogram, you can then accurately measure the distance between the peaks, and also you can get some idea of how those peaks are dispersed in Z. So then you can get a calibration with some uncertainty associated with it, and that uncertainty, of course, gives you some confidence in the calibration that you've done, right? So that's the preferred technique for a Z calibration. And then there's also an issue about non-linearity in the z-piezo. This just simply means is the calibration fixed for all values of Z, extension of your z-piezo. And the way that's often done is by machining a wedge with a known angle alpha. You then mount this grating that we used in the previous slide and on this wedge. And because you know the angle alpha, then you know that the height differences between the different features on that calibration grating. And so what you can then do is you can measure the height as a function of Z, and you've got a variety of different possibilities, right? If you find that the height feature is basically constant, independent of the feature number, then you can conclude that your piezo is linear in Z. But on the other hand, if you start to see a systematic increase, let's say in the height as a function of the feature number, that would indicate that your calibration of the z-piezo depends on the actual voltage that's applied to it. It's not just one number that you would need to take into account. So this is a useful technique that allows you to check things in some detail. If accurate Z height measurements are an issue for you. So I'd like to end the lecture with a warning, I guess, because very often you may be using an atomic force microscope that's located in some central facility, and it's a multi-user AFM, so many different users are coming and going. I always get nervous when that situation arises, because I always want to know when the calibration was last checked. Very often the calibration numbers are embedded in the software of the instrument. A user could inadvertently change those calibration settings without you knowing it, so that if you do not run a separate calibration check, you start to believe numbers that come out of the instrument, and those numbers could be in fact off. So I think it's important, if you're associated with a multi-user AFM in some central facility, I think it's important for you to constantly be asking, when was the calibration last checked? Who's doing the calibration checking? Right? If you don't do that, I'm afraid you may get numbers out of your instrument that may not be as accurate as they could be. So the next topic that we're going to discuss are going to be contact mode scans. So we're going to actually now put the tip in contact with the substrate. We're going to start to raster the tip across the substrate and talk about the images that are produced. So we'll see you when that lecture begins. Thank you.